All right, 9.5, a continuation of all of these different tests for finding out if series converge. And this one is called the alternating series. So we're going to take a look at theorem 914, and it says the following. So if the a sub n value is positive, and we have a series that goes back and forth between positives and negatives, so it has a negative 1 to the n factor there. So that's going to make every other term positive, every other term negative. So it's very specific, right? Because there could be things that have positives and negatives in them, but this one is alternating literally. Then this will converge when, number one, the limit is 0. The limit of the sequence is 0. Now, that's important because that's not enough in general to do this, right? If we just had the limit of the sequence being 0 for just any old sequence, it doesn't always work. We saw that one with the harmonic one. Right, the harmonic series has the limit as 0 and it doesn't converge. Okay, so this matters that we're talking about this type of a test. And then the second thing is that the subsequent terms get smaller each time. They're decreasing. So a sub n plus 1 is less than or equal to a sub n for all n. And if either one of these issues are not happening with this alternating series, or the limit doesn't equal 0, or the sequence is not decreasing, then this is going to diverge. Now, this is actually a really nice test, at least the first condition is, because it sort of feels intuitively right, especially in the way that they don't seem to be when we look at the harmonic series, right? The harmonic series feels like it should converge because it decreases, but it doesn't. It doesn't converge when it does that. So this one will, so that's very nice. The second condition is a little harder to test, but we've done it already before. We did it back in section 9.1 where we looked at things where monotonic, specifically decreasing or increasing. So we've seen how this works. We'll see how it works again. All right, you ready to take a look at some? I think that everything else is examples. So, all right, here's an example. First one. Determine if this converges or diverges, right? And there's two conditions. And to be honest, the first condition is easier, so we should test it first. Because if it fails, we avoid testing the harder condition, correct? Okay, so the first conditions we're always going to start, not just because it's number one, but honestly because it's a simpler one to check. So if we test the first condition, it means we're taking the limit. Notice first, I should say, this is an alternating series, right? Because I've got the same form. The negative 1 to the n alternates, goes back and forth between positives and negative. And then the n squared over n plus 1, those are always positive. That's what it takes for it to be an alternating series. So it does fit the criteria. All right, so we're going to take the limit of the part that doesn't include the negative 1 to the n. So the limit of n squared over n plus 1.
What do you mean, like, for the second part, is it n squared over n plus 1? That's always going to be positive.
This is a positive number because the n's are positive.
Okay, and so how does it, the both parts have to be alternating then, or just one of the parts?
The only part that's going to alternate, if it's an alternating series, then you're going to have this piece right here. It's going to go back and forth.
Yeah.
Okay, so that's going to for sure happen. And this piece can't be negative.
Okay.
Yeah, that's the conditions that we started with over here. We've got the series is positive. And then this part right here makes it alternating. The negative 1 to the n makes it alternating because the other part is positive. It has to be negative something. So like let's say you had negative 2 to the n. That's okay because you could separate it out and make it negative 1 to the n and 2 to the n, and then you're good to go again. So one part of it's the alternating. So it doesn't really matter that it's negative 1 because you can separate it so that it would look like that if you wanted to. Yeah. Okay.
So one part has to be negative that's raised to a power.
Yes, a negative number that is raised to the power n. It has to be raised to something that alternates. So like if you raised this to the power 2n, it wouldn't necessarily work, right? Y'all with me? It would always be positive, right? So it really does matter that the n is alternating. So your exponent could be n, your exponent could be n plus 1, but there are things your exponent can't be, right? Okay. Most of the ones you're going to encounter are going to look like this. They're going to have a negative 1 to the power of n, or a negative something like you mentioned, Connor, to the power of n. All right, back to my limit. Y'all good? What is this limit as n goes to infinity? What is it? It's infinity. How come, Adam?
Because it's n squared over.
Yeah. Yeah. So you've actually said two different reasons that we've thought about probably before. The exponent on top is bigger than the exponent on bottom. So if you're thinking about this from an algebra standpoint, the top is going to dominate. That's going to go to infinity. If you're thinking about it from the limiting aspects that we've been working with, we would be dividing by 1 over n. You could do 1 over n squared if you wish, but 1 over n works as well. And if you do this, you end up with n still on top, and then you have 1 plus 1 over n on bottom. So this one goes to 0. We still have n on top. If you decide you wanted to do it squared, let me just write it in so you can see what happens. If this said n squared like that, what we would get is we would get a 1 on top, and then we would have 1 over n and 1 over n squared. And the problem at this point, if we think, not problem, but the way that this ends up not working is that these both go to 0, which means the entire denominator is going to 0. So while we cannot say that 1 divided by 0 is infinity, that doesn't make sense. Number one, you can't divide by 0, and number two, things can't equal infinity. What we can say is that if you divide 1 by something that's getting infinitely smaller, the whole fraction gets infinitely bigger. So either way, from the first way I wrote it or from this one, this limit's infinity. Do we need to test condition number 2? No. What does this tell us? It diverges, right? So this is an alternating series. So this alternating series diverges because the nth term, or let me just say it, let me say it differently. Let me say my limit. The limit as n goes to infinity of n squared over n plus 1, it's not 0. Now that's the kicker, right? It's not 0. And if it's not 0, by the alternating series test, the summation from n equal, actually, I think that's good because I wrote it at the beginning. I forgot it backwards in my notes of how I've written it, but that's fine. This alternating series diverges because the limit of the positive part, the n squared plus over n plus 1, does not equal 0. And it's the alternating series test that tells us that. Okay. Straightforward enough? It's probably worth noting that this actually says, actually, let me look over here at this one. It says that the limit has to equal 0, right? It doesn't say that the limit has to be infinity. Did you notice that? So if you had gotten the limit as, say, 2, that would be a finite limit. That would be okay, but it still wouldn't meet this criteria. You really need to see that it's not 0. It doesn't have to be infinity. In fact, the limit doesn't have to exist at all. Imagine what would happen if you have a sine graph that's shifted up. It's got to be positive. But imagine you have the sine graph that's all above the x-axis. Well, it would be all positive values, right? And then you've got this negative thing in front that makes things alternating. So you've all got the positive values, but its limit doesn't equal 0, so it still wouldn't work either. Yes?
Is there ever a case, or rather than
At least not with this test. Sorry, go ahead.
Is there ever a case where taking a integral of a sub n would be better than doing a limit?
So there are some cases where you have options on which test you do. I will say that the majority of the time, oops, I was on the screen I want to be on. The majority of the time when you see that -1 to the n, it's going to be an alternating series test that you're going to do. Because we don't have a lot of good ways to deal with that -1 to the n portion of it inside of our other tests.
Gotcha.
Yeah. Now, that's not exactly a perfectly true statement. You'll see when I post the video for Friday that the ratio test, I think, actually works pretty well in those cases as well when you have things that are alternating. But this one right here is sort of our default when we see that -1 to the n. This is at least what we try first. Okay? All right. Let's try another one. So this one is the summation from n equal 1 to infinity of -1 to the n and then 2e to the -n. So let's first make the sort of awareness of, does it actually meet the criteria of an alternating series? So it's got that -1 to the n. We can all see that one. But this is the part that I want you to be careful of, because it looks like there's a negative in there. Is this really a positive number?
Yeah.
It is. How do you know?
Yeah, well, if n was negative, it's a negative to make it
Okay,
positive.
but n's not negative. N's are always positive, so you don't have to worry about that case.
Well, in that case, it's multiplied by 2, so the number that he's going to become positive.
But if you actually had something that was negative multiplied by 2, that wouldn't fix it. Okay? Okay, so yeah, so Adam is saying, and he's right, if you think about what negative exponents actually do, they don't make things negative. They move things to the denominator. So if I were to rewrite this with a positive exponent, it would look like that, right? Okay, so if this is what I actually have, or it's written in this way, as n goes to infinity, it's easier to sort of think about what this graph maybe is doing in terms of its actual terms. It is positive, right? If I have e to a positive power, e to a positive power is always going to be positive, and 2 divided by a positive number will also be positive. Okay, is that all right? Okay, so what's the first condition that I need to test then? The limit. So we're going to do the limit as n goes to infinity. I'm going to use the rewritten one that I have, that version of it, instead of the original one that they gave me. So, do you know what this one's limit is? It is 0. How can we justify that? I mean, you can look at a graph to kind of see what this graph looks like, but you probably don't really know what the graph off the top of your head of 2 over e to the n looks like, true? I don't know what it would look like exactly. I do know it's infinite. I mean, the limit goes to infinity, but is there a portion of this that you do know what it looks like? You know what the top looks like. You know what the number 2 would look like if you just graphed y equal 2. You know that part, right? Do you know what the bottom would look like if you just graphed y equal e to the n? Okay, so let's actually, if you don't, grab your calculator. If you do, I'm going to sketch it. But if you're looking at me and you're thinking like, I don't remember, that's okay. Just grab your calculator. See if you can take a look and see what that looks like, and then I'll sketch what you guys have. So I'm asking you just to graph y equals the e to the n part. Okay, what does it look like? Yeah, it's an exponential graph, right? So this is an exponential graph that looks like this. Does that look familiar? I mean, it's crossing at 1. My graph's not super believable, so I'll mark it as though it were. This is getting infinitely large, right? So if I were actually looking at the limit of just the denominator, this limit's infinity, true? And if I have something that's getting infinitely large in the denominator, then the whole fraction is getting infinitely small, still positive, so close to 0. Okay, so as we're taking a look at saying that this limit is 0, we can actually say that this is happening because the limit of n to infinity of the denominator e to the n is going to be infinity. Okay, so break it into something that's a familiar graph. This is a familiar graph. It's from chapter 5. It's the first thing we did in Calc 2, for those of you who have taken Calc 2 here. All right, so cool. We actually have this happening, right? We've got first condition met. So here it is right here. That's my first condition. What is my second condition? A sub n plus 1 is less than or equal to a sub n. Okay, are you good with that? So we're going to write out what those would look like for this particular sequence. So it is the sequence pieces that we're looking at. So this is 2 over e to the n plus 1. And I have 2 over e to the n. I want to be able to say it's less than or equal to in between. Like, that's the goal, right? But I need to be able to justify why that happens. So if I were to take the left-hand side and manipulate it just a little bit, we'll get to this in a second. How could I change this left-hand side so that it looks a bit more like 2 over e to the n? Think about properties of exponents. Okay, what would I multiply, Sophia? Good. E to the n times e to the, I'll write the 1, but we recognize that's just e, right? That's property of exponents, sort of used in reverse. We usually think about that property going the other way, where we have the e to the n times e, and then we add the exponents together. Nod your head if you remember what I'm talking about. Okay, good deal. All right, so this right here, is it bigger or smaller? Just look at the denominator. Is this denominator bigger or smaller than this denominator? It's bigger, right? How do you know it's bigger? Because there's an extra e in the bottom, right? And e is approximately 2.7. Okay, we'll just say 2.7, right? It's 2.718 if you want to use more, but it's bigger than 1. Now, it matters, right? It matters here that this says e, right? If this had some other number, like the number 1/2 or 0.5, this would not be a true statement. Are you guys with me? It's because this number e is bigger than 1 that actually makes that denominator bigger. So the denominator is larger on the left than it is on the right, which means the fraction would be smaller on the left than it is on the right. So this is less than or equal to this. And the reason really is because e is greater than 1. I've multiplied by something in the denominator that's greater than 1. It makes the whole fraction smaller. Okay, condition 1 met. Condition 2 met. What does that tell me? It converges. So I'm going to need some more space to write something somewhere. So let's actually, let's do this. I'll shift this over here. Okay. So by, by the alternating series test, you're going to see me abbreviate some of these tests. This is a good one, AST. By the alternating series test, the summation from n equal 1 to infinity of -1 to the n 2e to the negative n converges. So each time you have to answer the question of something converging or diverging. And I know in this section in particular it's going to feel a little bit silly because everything's going to be by the alternating series test. But keep in mind where we're headed. We're headed to a point where you're going to have to pick a test. So I want you in the habit of saying every single time what test tells you that this works. This test is the alternating series test. Okay?
So like on the test, you want us to say which test we use?
Mm-hmm.
Just do you want us to rewrite the equation or just say which test we use?
You could say by the alternating series test this series converges. That's fine. I don't care. But you need to say that it converges or diverges, or if it's not determinable, we'll see some cases of those later on. And you need to be able to say by what test. You got to have the test every time. All right. Let's take a look at the next. All right. Sometimes a series may have both positive and negative terms, but it's not alternating. So I kind of mentioned that before, that we needed to make sure that it really had to go back and forth for it to be alternating series. So here's an example. The graph, or the equation, of the sine of n. It goes between positive and -1. Agreed? Right, that's what sine does. Sine bounces up and down between positive and -1. And it does it at certain intervals, but they aren't the whole number intervals, right? So if I did sine of 1, sine of 2, sine of 3, sine of 4, it's not always going to go positive, negative, positive, negative, positive, negative. Sometimes I'm going to get a couple negatives in a row, or a couple positives in a row. So this one has positive and negative terms, but it doesn't alternate. So one way to gain some information is to consider what happens to its absolute value. By the direct comparison test, which we've saw was last time, wasn't it? That was our last one. The absolute value of sine of n over n squared is less than or equal to 1 over n squared. True? Does that statement make sense? The numerator is between -1 and +1. The denominators are exactly the same. So whatever value I get is between -1 and +1, so it's less than 1. By the p-series test, we know that second term, 1 over n squared, converges, right? The summation of it will converge. So the summation of n equal 1 to infinity of 1 over n squared converges. Thus, the absolute value of sine of n over n squared also converges. Now notice, that didn't say what happened to this. It said what happened to the absolute value of it. Did you catch the difference? If you didn't, do you catch it now? Okay, so we're alternating. We're altering is what I wanted. We are altering something to see what we can tell you. I cannot use this technique that I had been using before with the series, that I've circled. It's not an alternating series. But if I put absolute values on there, I can use a different kind of comparison, using the direct comparison test, And with the absolute values on there, it will converge. So theorem 916 tells us that that's enough. So if the summation of the absolute value converges, then the summation without it converges too. That's not the alternating series test, right? So that's something else. It should have a name, and it does. You can see below, definitions. So the summation from n equal 1 to infinity of a sub n is absolutely convergent when its absolute value converges. And it is conditionally convergent when the summation of a sub n, that should say converges. That's funny, I don't have that word in there, converges. But the absolute value one does not. So notice what this is saying. This is saying that this is one of those like one directional things. If I know the absolute value converges, that's the theorem at the top, then the original series converges as well. But just because the original series converges does not mean its absolute value does. And I can give you a really quick, easy example where you're like, oh, right, yeah, that makes sense, and I will. We're going to take a look at that harmonic series again. If we had the summation from n equal 1 to infinity of negative 1 to the n times 1 over n, this would converge. Why would this converge? Yeah, the limit of the 1 over n part is going to be 0, right? It is an alternating series. It is oscillating back and forth, so that limit being 0, and it is getting smaller, right? Every term is smaller than the one before. So by the alternating series test, this would converge. But if I took the absolute value of that, what would this be the same as? Just 1 over n. And what do we know about the summation of 1 over n? It's harmonic. It does not converge, right? It diverges. So knowing the absolute value converges guarantees the original sequence converges, but knowing that the sequence converges does not guarantee it the other way around. So you got to make sure you know which direction you're looking at. Now, let's take a look at an example where these questions are sort of posed for us. Now, this is an alternating series. How do I know? What are some red flag things I'd be looking at? I got a negative 1 to a power. The power's not n, it's n plus 1, but that's okay, right? It's just shifted, right? Instead of like the even terms being positive, the odd terms are positive now, whichever direction. I may have just said it backwards, but it just switches whether or not the odds or the evens of the terms are the positives or the negatives. That's fine. This is an alternating series. So we're going to decide from this series if it's absolutely convergent, conditionally convergent, or divergent. And we start out by figuring out, does the absolute value converge? That's what we're going to do. So we're going to take the absolute value and see what happens. So if we take negative 1 to the n plus 1 over n squared, and I take the absolute value, what is that sequence, the part that's inside of the series, what is that sequence going to look like? It's just 1 over n squared. And I don't really need the absolute values anymore because n's positive, so automatically 1 over n is going to be positive, as is 1 over n squared. Will this converge? Yes, this converges. Why? That one will work. This converges by p-series. Is everybody okay with that? So since the absolute value converged by p-series, this is absolutely convergent. Now, I don't know if it's my next example or if I want to just go back to the one I just mentioned. No, I'll go back to the one I mentioned, then we'll go on. If I were doing the same sort of thing with this example that I sort of threw in here at the top up here, and I took the absolute value, it wouldn't work, right? That's what we did. this sequence, the one that's at the top, that series, I should say, the one that's at the top, it is not absolutely convergent. It is conditionally convergent, though, right? This does converge. It converges by the alternating series test, but its absolute value does not. So if I was categorizing this as absolutely convergent, conditionally convergent, or divergent, it'd be the one that's in the middle. It'd be the conditionally convergent category. It does converge if the -1 to the end's on there. It's by absolute value or by the alternating series test. But if you put the absolute values on there, it doesn't, so it's not absolutely convergent. Are we okay? Sophia?
On the test, would you ask for, is it absolutely conditionally?
I could. Yes, I could, for sure. You'll have some of your questions in this section that will ask you that kind of a phrasing, and then you'll have some that are more like over here where it just says determine the convergence or divergence. So if it just says it like this, it's not asking about the absolute value part of it at all. It has to actually say it in the directions before you want to throw those absolute values on there and consider it. Yeah. Okay, let's try another one. One more. Same directions, determine whether the series converges absolutely, conditionally, or diverges. So on this one, -1 to the n plus 1 over n times natural log of n. Let's start with, is it an alternating series? Yes, it is an alternating series. It actually looks a lot like that last one because it has that n plus 1 power instead of the n power. And we start out doing the same thing. We throw those absolute values on there and we try and figure out what's going on. Okay? So we're going to take the absolute value. Oh, this is a typo. This needs to say n equal. Does yours still say 1 or does it say 2? It should say 2. Yeah, mine says 1. It's changed in my notes, but it didn't get changed in the slide. Does anybody know why it can't say 1? Yeah, the natural log of 1 would be 0. I'd have a 0 in the denominator, so this needs to start at 2. It was just a typo. All right, we're taking the absolute value of -1 to the n plus 1 over n ln n, which looks a little funny, but that's okay. So if I simplify this expression, what will this give me after the summation symbol? Natural log of n, right? Yeah. Okay, so at this point, I need to figure out if that converges. I'm not testing its limit as it goes to 0. Like, this is not the alternating series test. I no longer have an alternating series, right? So I can't just say, oh, look, the limit of that goes to 0, which it does, right? The limit of this does go to 0, but that's not something that I can generally test. I was only able to do that with the alternating series test because the -1 to the n was there, and I just took it off. So I can't do that right now. So it probably is worth noting that this is going to be at least conditionally convergent. Because if that -1 to the n were on there, the 1 over n ln n, it is going to go to 0. All right, we may end up needing to test that and show that formally, but first we want to see if this one goes to 0. It doesn't go to 0, converges, what I'm going to say, converges. How can I see if this actually converges? What? Sorry, what did you say, Preston? Integral test, yes. I thought somebody said it, but I couldn't hear. Okay, yeah, this is the one that you guys watched last Friday, the integral test, right? So why did you think it was an integral test, Preston?
Because whenever I see a natural log and I also see a something in the denominator, I'm like, whenever u equals natural log, you can take away the thing in the denominator.
Yeah, so your mind immediately goes to u substitution, it sounds like, right?
Yeah.
There's a u substitution there. In Calc 2, we talk about the fact that anytime you have a natural log, you're going to either have u substitution or integration by parts because we don't have an antiderivative form of the natural log except for tables. There's one in a table. But there's not a closed form for it that's nice and clean that we memorize and so forth. So yeah, this is going to go with or turn into a integral test. So we're going to do our integral from 2 to infinity of 1 over n, we'll change it into x's, x ln x dx. And u, okay, I'm off my screen, let me write it underneath. I'll write it above. U will be the natural log of x. So what will du be? Yep, 1 over x dx. So if I make this change of variables here, this integral now will be, I can leave the 2 to infinity off for the moment, will simply be 1 over u du. correct? What's the antiderivative of 1 over u? Yeah, it's natural log of u. But what was u? Natural log of x. So there's a natural log of a natural log of x. It's okay? Thank you. Yeah, evaluated. Now I'm going to write it in here, and then I'm going to write it properly. This is how we're thinking about it, right? We're evaluating an infinity and 0, but you can't evaluate infinity. That's not a number. So do you remember what we did? This is one of the things that I'm changing the order of when I do Calc 2 this semester because I didn't like where the new book placed it. Yeah, we did a b substitution, and we did limits at the beginning. So we did the limit as b goes to infinity of the natural log of the natural log of x. And then I had a b on top, and I had a 2 on bottom. Alrighty. So now I can put the b in the 2 ends. This is the limit of the natural log of the natural log of b minus the natural log of the natural log of 2. And what I really care about is whether this is a number, that looks like a 6, kind of my b does, whether this is a number or whether this is infinity, right? So when I put infinity in here, or when I think about the numbers getting infinitely large, what is the natural log as the graph gets infinitely large, as the x value gets infinitely large? What is it? It's infinite, right? Natural log graphs get infinitely large really slowly, but they do get infinitely large. There's no bounding on them, right? They're unbounded. So this piece right here, all of this is infinite. This is a number at the end. So it's infinity minus some constant. I don't know what that constant is as its exact form, and I don't really care. If I have something infinite and I take a little bit away, it's still infinite, right? So this is still infinite. So what does the integral test tell us about this sequence that we were looking at to start with? It diverges, yeah. So, do I have space? I don't. I definitely needed a slide in this one. Okay. All right, so all of this is telling us then by the integral test, the summation from n equal to 2 of n equal 2 to infinity. And I'm going to go back to the original one that I had, which had the absolute values on it. Diverges. Right? The integral diverges, so the series diverges as well. That's what the integral test tells us. Okay, that means that I have eliminated the absolutely convergent condition or possibility, right? It's like multiple choice. I eliminated one of the 3 choices. I need to test the second one now, conditionally convergent. We already talked about the fact that this is going to work for conditionally convergent, and it is going to work because it's an alternating series. So the summation from n equal 2 to infinity of -1 to the n plus 1 over n ln n. All right, so condition number 1, the limit as n goes to infinity of 1 over n ln n. What happens to this denominator? The denominator gets infinitely large, so then that means that the fraction would be going to 0. So this goes to 0 because n times the natural log of n is infinite. Right? That's why. The denominator is infinitely large. The fraction will then go to 0. So that's condition number 1. Condition number 2 is a little bit trickier to test on this one. So we would want to see that when I do n plus 1 down here, and I take the natural log of n plus 1, that this thing is, what we want to test, right, is that it's smaller than or equal to 1 over n ln n. It's a little bit easier to just ignore the numerators and think about the denominators. As long as the denominator is bigger, the whole fraction is smaller. So n plus 1 is definitely bigger than n. True? Yeah, that's not a problem. We definitely can say that. How about the natural log of n plus 1? Yeah, it's also bigger because log graphs are constantly increasing, right? So in both those cases, n plus the graph of n and the graph of natural log n are increasing or strictly monotonic, strictly increasing functions. So since both of the denominators are bigger, both pieces of the denominator are bigger, this actually is satisfied. Okay, the denominators are bigger, the fraction is smaller. So since number one, the limit is 0, number 2, it's decreasing. That's what I just found. It's a decreasing function. What do we know? It is conditionally convergent. So it's by what test? Yeah, we were using the alternating series test. Okay, so by the alternating series test, this converges. So it's conditionally convergent. That's a terrible looking screen. I so apologize. I really need another slide in there. Okay, are you guys good? Ben says no. It does. It looks really messy. So maybe this one thing maybe this tells you is that if you're one of those people who likes to like skip a problem when you aren't sure how to do it and go back to it, skip a fair bit of space. It might take you some space. It might not. You might end up with some dead space there, but better than crammed it all in. So, okay, we have one more. Are you ready? Okay. Same directions. There were 3 things, right? Absolutely convergent, conditionally convergent, and divergent, and we've seen both of the 2 first ones, right? So we probably expect, since I'm showing you different options of things that happen, this is an example of the 3rd. This is going to be one that diverges. Okay, y'all ready? Okay, so we start with absolutely convergent, and so we would take the summation from n equal 1 to infinity of the absolute value of -1 to the n plus 1 times 2n plus 3 over n plus 10 with the absolute value. It is an alternating series, right?
Yes.
Yes, because we have that -1, in this case again to the n plus 1. It is an alternating series. And then the 2n plus 3 and the n plus 10 are both positive, so that fraction, that ratio is also, that sequence is also going to be positive. All right, so if I take the absolute value, I actually have the summation from n equal 1 to infinity of 2n plus 3 over n plus 10. True? Okay. Why?
Because at n equals 7, they're equal, and then once you get past n equals 7, the top will always be greater because 2 times n will always be greater than n.
Okay, so this diverges. There's a test that we can use though. So you're not wrong, Adam, but there's a test that will simplify your description. Why is this going to diverge?
The ratio test.
We aren't at the ratio test yet. What's that? What if I do a limit? So why would a limit help me here, Ben? You're right. I like the idea of doing a limit here.
Because you can move some stuff around and make some zeros.
Okay, so if I have 2n plus 3, and then I'm over n plus 10, what would you like to see us do next? Okay, so we're going to multiply by 1 over n or divide by n on top and bottom. If I do that, I'm going to get the limit as n goes to infinity of 2 plus 3 over n over 1 plus 10 over n. And like you said, a couple things go to 0. What is the limit here? The limit's 2. Now, there's nothing wrong with it having a limit of 2 per se, but that still tells us that it diverges. Why? Because it's what?
Because L is greater than 0.
Yes. What test, though, is what I'm asking. Mm-mm.
Just about power
No, come on, just everything. Gotta get one.
Nope.
Oh.
The divergence test is absolutely fabulous. We don't see it used very often because typically we have these sequences having limits of 0, right? Most of the ones we do, and a limit of 0 in a sequence doesn't tell us it converges or diverges. It's an extremely unhelpful fact. So in certain conditions it's helpful, but as a general statement it's not helpful because that, like that harmonic series that showed up, right? You know of things that the limit is 0 and it diverges. So However, but the contrapositive of that is actually very helpful. If the limit is not 0, like this one, then it means that this does diverge. And if you think about the reason why, summations are adding things together, right? What this is telling us is that eventually we're consistently adding something that's got about a 2 together. And if you add 2 and 2 and 2 and 2 and 2, and you never stop adding 2, that's going to be an infinite quantity, correct? But when you add things that get infinitely small, it depends on how fast they get infinitely small, if it actually levels off or if it doesn't. So when the limit is not 0, which this one's not, the divergence test tells it diverges. All the divergence test can do is tell us when something diverges. It can't address convergence at all. So this will diverge by the divergence test. So what does it mean? It's not absolutely convergent, right? Now, the interesting thing, because this particular problem is what it is that the second half of this, when we test for conditionally convergent, is going to feel very similar. You ready to take a look at the conditionally convergent part? I have a blank screen here, but I can make it something at the end that I can write on. So let's go with, how about a chalkboard? Okay, so if I want to test the conditionally convergent, right, because that's where I am now, then I'm going to test to see the summation from n equal 1 to infinity of negative 1 to the n plus 1 over 2n plus 3, times 2n plus 3 over n plus 10. And this is a what kind of series? Alternating series. So I'm just going to remind ourselves. So what is the alternating series test thing I have to do? Well, the first thing is I want to test the limit. The limit of what? 2n plus 3 over n plus 10. And we've already done that, haven't we? This is 2. I'm not going to write it out again because it's all the same steps. We've already tested that this limit is 2. What does that tell us by the alternating series test? Right. So this diverges by the alternating series test. So it is not conditionally convergent, right? So it's not absolutely convergent. It's not conditionally convergent. Therefore what? That little symbol means therefore, by the way. It is divergent. It is a divergent series because it was not absolutely convergent or conditionally convergent. Okay. Any questions on those? So there's going to be basically 2 types of questions. Don't overkill on what the questions ask. Make sure that you're testing what you're supposed to be testing, right? If it doesn't ask about absolutely convergent, don't test for absolutely convergent, right? Don't go doing more than you have to.